Hello and welcome to the Advanced Reaction Engineering live session. The last week we discussed about the tanks and series model for the non-ideal flow reactors. So this week we'll discuss about the dispersion model. So there are two methods basically which we use for testing or its inclination towards ideality. So one is the tracer test and is a reaction in a reactor. So for tracer test, the dispersion model is used to describe the non-ideal tubular reactors. So if there is an axial dispersion of the material, which is governed by an analogy to the fixed law of diffusion. So what is the fixed law of diffusion? It's the minus dAAC dCdZ to transport by bulk flow UACC moles per second. And so every component in this mixture, what will be happening? It will be traversing through any cross section of the reactor at rate equals to this particular which we generate from the fixed law of diffusion, and this will be resulting from the molecular and convective diffusion. Okay, so if you see, this is the standard plug flow where there is no difference between each of the molecules, but if there is a dispersion of the reactors, then it's problematic. Okay, so there are certain molecules which will be diffusing forward, which will be lagging behind. So there will be concentration profile different with and without dispersion. So that was why we need the dispersion model, which will calculate the dispersion profile. We'll have to see how dispersion affects the concentration profile in a tubular reactor. Some molecules will diffuse forward ahead of the molar average velocity, while others will lag behind. How dispersion affects the concentration profile in a tubular reactor? So we consider the injection of a perfect dispersion causes the pulse to broaden as it moves down the reactor and becomes less concentrated. So we consider the injection of a perfect tracer pulse, and you have to see that this particular dispersion, it will be causing pulse to broaden as it moves down the reactor and it becomes less concentrated. The molar flow rate of tracer Ft by both convention and dispersion is del CT del Z plus UCT multiplied by AC. Okay. To better understand how the pulse broadens, the concentration peaks T2 and T3, a concentration gradient on both sides of the peak causing molecules to diffuse away from the peak and thus broadens the pulse. Okay. So if you see here, the pulse broadens from T2 and then it moves towards the T3 position. And then what will be happening? So if you substitute this particular mole balance equation, minus del F del Z equals to AC density del T, substitute for Ft and divide it by the AC cross-sectional area, we'll be getting this particular equation of dispersion. And the second approach is okay. So you have to find the dispersion coefficient. So mole valence equation of TFR is required. A mole valence is taken on a particular component of the mixture over a short length delta Z of a tubular reactor of cross section AC. To arrive at this particular equation, minus 1 by AC dF dz. So if you combine this mole valence equation number 3 and this particular equation of the molar flux Fa, so you'll getting this equation minus 1 by AC dF dz plus Ra equals to 0, which will be coming to this equation from the fixed law of diffusion dA by U d2 Ca dz plus Ra by U equals to 0. So ultimately, so if you see the molar flow rate F in Z direction of a tubular reactor, Faz equals to ACWAZ. The molar flow rate Faz equals to ACWAZ equals to minus DAB dCdz plus CAUZ AC. So the entire equation is dispersion plus flow plus reaction. This is the entire regime. So what is in the dispersion regime? We've seen in the dispersion regime. If you see the equation 4 is responsible to an analytical solution. Okay. So what is that particular analytical solution? So we'll be having this particular solution where we consider psi equals to Ca by Ca naught, lambda. And from this equation, the earlier equation 5, and using this particular approximations, we'll be having the number 6 equation, okay, which is 1 by PER d2 psi d lambda square minus E psi d lambda minus equals to 0. This dA is Damkohler number and 1 by PER is the vessel dispersion number. These are again some characteristic of this particular non-ideal reactors, which are unitless and dimensionless numbers. Okay, so this Damkohler number is rate of consumption of A by reaction divided by rate of transport of A by convection equals to K tau equals to K Cn0 to the power n minus 1. Okay, so similar kind of another dimensionless number is the Peclet number, which is the rate of transport by convection by rate of transport by diffusion or dispersion. Okay. Similarly, you can also determine the Darm-Colon number by experimental observations in this particular way. So the unsteady state pressure balance, as we discussed earlier, this will have to do for experimental determination of this dimensionless number. This is an example of a tracer test, and what is the method of injection of the tracer is the pulse injection. So find the dispersion number dA or the Peclet number using the tracer test. What is the equation? This equation is this: 1 by Peclet number d2 psi d psi d lambda equals to d psi d theta. Okay. So the steady state flow of A will be giving you as 1 by Peclet number, and this particular basically is a similar formula. What you will have to do is just make it in terms of the Darm-Colon numbers. Okay. So there are two types of boundary conditions here. One is the closed vessel, one is the open vessel. An analytical solution for the first order reaction in terms of the Peclet number and the Darm-Colon number. Okay. So for the closed vessel system, the assumptions are there is no dispersion or radial variation in concentration either in the upstream or downstream of the reaction section. The to dispersion are imposed on the plug flow velocity profile, and the open vessel situation, the dispersion occurs both upstream and downstream of the reaction section. A closed open vessel boundary conditions is one in which there is no dispersion in the entrance section, but there is dispersion in the reaction and exit. Yeah. So ultimately, you have to solve this particular equation I'm showing here. So you'll have to solve the equation, and ultimately you'll get CA naught equals to minus dA by U del CA del Z, Z equals to 0 plus CA 0 plus, based on the Danckwert's boundary conditions. Okay. So for the closed vessel system, at the exit to the reaction section, the concentration is continuous, and there is no gradient in tracer concentration. So the two boundary conditions is at Z equals to L is CA naught L minus equals to CA L plus, and del C del Z equals to 0, and at Z equals to 0, CA naught equals to minus d by U del C del Z plus CA. So at lambda equals to 1, d psi d lambda equals to 0. Yeah. So the dispersion model comes to this: 1 by Peclet number d2 psi d lambda square minus d psi d lambda equals to d psi d theta. So the first moment is the mean residence time equals to tau. Second moment based on the variance, chi square means variance by mean residence time square equals to 1 by tau square, 0 to infinite integration t minus the whole square e to dt. Okay. So putting these values in our equation 3, which is this one, the analytical solution comes as this: chi square, sorry, sigma square tm square equals to 2 by Peclet number minus 1 by Peclet number square 1 minus e to the power minus pr. So you have to find the dispersion number. So based on the dispersion model, which we have discussed earlier, if you see this particular graph, so this middle line is based for the plug flow, which is d by ul equals to 0. The right line is for d by ul equals to 0.002, which means that there is a small amount of dispersion. And remember, this graph is based on psi versus theta. Theta is t by tau. Okay. And this mixed flow means the d by ul will be infinite. Okay, so this particular above equation has been solved here numerically for a pulse injection, and the dimensionless effluent pressure concentration psi, which is shown here as a function of the dimensionless time theta, which is equal to t by tau for various Peclet numbers. Based on these Peclet numbers, t by ul, you can find out what is the category of dispersion in your reactor. It's as low as this particular Peclet number value will be, the reactor will be more towards the ideal plug flow reactor. As high as like entirely infinite, it means that uh, it's entirely a mixed flow, or as low as 0.002, it will be having a small amount of dispersion. 0.025 means intermediate amount of dispersion, and zero point 0.2 is large amount of dispersion. These are some example values are shown here. So okay, and so this will be the final dispersion model uh, slide here today. Uh, so these things we have already seen. So this is the relationship between the mean residence time and the variance. Psi square by tm square equals to 2 by Peclet number minus 1 by Peclet number square into 1 minus e to the power minus pr. So I've seen this particular graph and the slide same as earlier. So for the closed vessel system, I have seen. Now for the open vessel system, we have to see. Okay, so both the boundary condition and the open cases. So we call it as a open boundary conditions. So 1 by PER e2 psi d lambda square minus d psi d lambda equals to d psi d theta. So concentration psi of at the location of 1 theta equals to Ct L comma T divided by Ct0 equals to 1 by 2 square root pi theta by p Peclet number exponential of minus 1 minus theta whole square divided by 4 theta by exact number. So mean residence time for an open system is Tm equals to 1 plus 2 PER to tau. So if to calculate for an open system where tau is based on the volume between z equals to 0 and z equals to L, the mean residence time for an open system is obviously will be greater than that of a closed system. So due to dispersion, the Tm will be greater than tau. The variance chi square by tau square equals to 2 by PER plus 8 by PER whole square. Okay. So case 2, if the space time tau is unknown, Tm and sigma square from Ct versus T data, find tau is in equation A, substitute tau in equation B to solve Dirichlet number R, and known PER, use equation A to find tau and V, the dead volume, which will be the difference between the measured volume and the volume calculated from RTD. So it's not always possible to inject tracer pulse cleanly as an input system. It takes a finite time to inject the tracer. When the injection doesn't approach perfect pulse input, the difference in the variances between the input and output pressure measurements are used to calculate the Dirichlet number. So delta psi square equals to psi in the square minus psi out square. So psi square Tm by Tm square equals to 2 by Tm. Finally, flow dispersion, and now the reaction part. So by reaction experimentally, we have to see determine the dispersion coefficient. Again, this small equation we have to write down minus 1 by AC d to dz by plus Ra equals to 0, d by u d2ca dz square minus dc dz plus Ra by u equals to 0, dfaz dz equals to Ra, and concentration of the flux is Waz equals to minus TAB TC dz. So d by u equals to d2ca dz square minus dc dz plus kca by u equals to 0. So from equation 5, 1 by Peclet number d2 psi del lambda square minus d psi d lambda minus dA psi equals to 0. Rate of consumption of A by reaction, rate of transport by A convection equals to K tau equals to Kc naught to the power n minus K1 L by U. So at the end of the reactor, as lambda equals to 1, solution concentration is this or this. Okay. So study until this today. See you next time.